back, everybody. I'm going to cover a handful of subtopics, so I'm going to have to be brisk, and I'm not going to be able to go into as much depth as I'd like to, but I think it's probably in the wide variety of the skills of the audience to kind of cover a wider variety of what we had done last year at Hess. So in previous work, we had focused on doing finite difference wave propagators with a reverse time migration in mind. We had worked on a collaboration with NVIDIA. This resulted in some CUDA kernel codes, very similar to the finite difference kernel discussed by Polyus and NVIDIA and GTC in 2009. We had a focus on the first generation of Tesla GPUs. So for example, we weren't able to make use of peer-to-peer at the time, so we used MPI for communicating your ghosts and your decomposed neighboring domains. We also ended up with somewhat of an add-on or bolt-on infrastructure. So we started with CPU kernels, then you move into GPU kernels, and you go from isotropic to VTI to TTI, and then you maybe even change your imaging condition along the way. It was tough to take those codes and extend or reuse them for FWI or least squares RTM, which are more hot topics today. And to compound on this, we had developed a code for optimizing the coefficients based on your subsurface model. And it would be nice to include these into these other applications that use wave propagation. So a little bit of a background on the previous kernel designs that we had. I would call this like a single pass stencil kernel. This is the same one that I was previously talking about what Polyus gave at GTC in 2009. This link that you see at the bottom, though it may not be there long enough for you, that was still valid as this morning. I don't want to go too much in depth on this. It's just to kind of give you a placeholder in the future of this kind of idea of your stencil. We also did wave field decomposition, specifically along one axis direction. That saves on communication time when you have to communicate your halos. So if you take your wave field, you break it down to two chunks. You need to store extra time and have communication to store your neighboring domain for the size of your stencil. But our current focus, it's not that any one of these was more important than the other. They were tossed around for actually, I'd say, a couple years. What do we do? So we wanted to really involve all of these in our redevelopment. So if we start here with portability, our primary focus was hardware portability. There are other accelerators on the market. There will be other accelerators beyond that in the future. And if we're going to spend the time to develop new code, we wanted to try and mitigate the risk that we'd have to redevelop again based on some new architecture or software. And the way that we handled portability, we used Akka. Now, Akka has been discussed at this conference several times in several years past. And the idea is you can write your kernel once in a higher level language, and then you have an API that allows you to interface with your memory and your device, and you can output variations of different kinds of binaries from CUDA to OpenCL to MP to just serial CPU binaries. You can even output these if you want to by flags into the software language itself, giving you a little bit of software portability, but ultimately you open up the path from CPU to GPUs, and if there were future accelerators, that could be put on the back end as well. We also wanted to improve our infrastructure. We wanted to be able to make it easier to reuse this code. We don't know what other applications may come up. We know that FWI is there. We know least squares RTM was there. So we decided to take a design approach of bootstrapping and modular approaches, kind of very old ideas for coding in C++ or object-oriented. I would call this inheritance and interface or template design. So if we start here with the TTI propagator on the outside, it can reuse much of the exact same code that's inside VTI. So instead of reinventing the wheel, just reuse that code. And so inherent VTI propagator. And then the same for isotropic, the VTI can reuse much of that code as well, so inherit from that. And then if you have your isotropic propagator inherit an interface propagator, this is where you can start to lead in some ideas of modularity and being able to use this in multiple wave propagation type applications. So, and staying with the modular approach, let's say you have multiple finite difference kernels. Now, you can have multi-pass kernels are out there, different boundary kernels, whether you want like absorbing or random or reflective, or you want a PML, and you have different types of source injection. As long as you build around the idea of the interface, you end up kind of building these objects of a propagator type. So they have an interface, whether you have isotropic or VTI or TTI. You can do others. It's just those are the ones I think that would relate most commonly in the audience. So if you have RTM or least squares RTM or FWI, some of these can reuse the exact same propagators. Or let's say you want to go from isotropic to TTI or something. You just want to just use that. As long as you have an interface that's common amongst all of them, you just kind of drop them into place, so to speak, conceptually speaking. Now, there are several generations of GPUs have come out since we first did our code. The cluster that we had several generations in there, and we wanted to take advantage of some of the computational improvements that we could get from newer hardware. So one of the easier wins that we could get is doing peer-to-peer communication. Before, we were using MPI, so we were coming from the GPUs down into the CPUs and then back to the GPUs. We also can now overlap with asynchronous communication. So while we're communicating, for example, the ghosts between your domains, you can hide that with computation. So if we kind of come back to this diagram, you can start here by computing what will be your neighbor's ghost or the edge of your own domain. And while you're switching these or flopping them, you can then start to compute the rest of your domain. And as long as this is computationally heavy enough, you kind of hide this latency of communicating. And that's an easy win to get better performance. I think that's pretty common. Others, I think, had already done it. Then we also wanted to take advantage of the increased hardware resources, so you had more register space, more shared memory. Pretty simple. Those combined between taking advantage of peer-to-peer and overlapping and the extra hardware resources, we think we got somewhere around about a 2x performance increase on the newer versions of the kernels, even though we were staying with single pass. But because we also stayed with a modular design, it made it easy for us to, down the road, put in something like a multi-pass kernel. So I say best of practice out there is this kind of multi-pass is where you're doing your cross derivatives, for example, in TTI, and 2 separate or 3 or even more kernel passes. And our intern who started this, Arturo, who is a PhD candidate here at Rice, he was actually able to, we still had time left for him to do a prototype TTI kernel. And we got about another 2x performance improvement just on top of that. And this kernel also incorporated some improved numerics, which I'll discuss here shortly. But first, I'd like to show you some performance. Just to remind people, or if you don't know, as we move from isotropic to VTI to TTI, we're increasing with arithmetic intensity. But I also tested on 1, 2, and 4 GPUs and when possible 8 GPUs. So what you'll start to see is you're having more communication that you need to try and hide. So if we are computationally or memory bound on 1 GPU and we need to double our domain, the idea is if we successfully hided this, so we're moving to a new software design element for inheritance and for modular design, but so we want to make sure that we're still maintaining good high performance computing. So we're after weak scaling. So this is probably, it's a fairly complicated plot, so I'll take a little bit on this and then I'll move into the VTI and TTI. Right here, what we have is space-time grid points per second per GPU. So we're computing a 3D volume, but we're taking time steps. Now, if we're doing this per GPU, because we're doubling the size that we start off with here in 1 GPU, but we're doing it per GPU, if we had perfectly weak scaling and we're hiding all of our latency, we should see a nice straight line. Obviously, down here on the Fermi, we're having a problem. I think this is because it has only 1 asynchronous copy engine. As you get up here to the Pascal architectures, you can see from 2 to 4, even on the P100s and the DGX, we have some drop-off, especially from 4 to 8. We have them on the PCI Express as well. But you'll notice I have these L's on here. I just held the part of the domain that we're sending across to other GPUs the same, and then increased the computational size of the domain to see what we were seeing, if there was a trade-off between keeping the GPU busy or not. And you can see by these curves that, yeah, what was happening is latency, the computational time was too fast, or we weren't hiding the latency enough. So we move it to something more computationally intensive, and you start to see that these curves flatten out. You actually see that the Fermi right here is now above the K10. We see some separation on some Pascals on the P40s and the P100s. The P100s have significantly faster memory. As you move to VTI, you're handling more attributes per your wave field, so you're using the local memory more often. You even use more when you go to TTI, so you see even bigger separation. And again, you're starting to see some of this flatten out just a little bit here as well. Just really quickly, if you wanted to see this, the idea is because we're going to use this for multiple wave propagation applications, this is kind of the ending of one time step of the propagator, and then the next time step here, this is some communication where I'm pulling off the receivers. So for FWI, this might be useful, but maybe it's kind of hard to see, there it is. Maybe in the case of, you're doing RTM, you need to take more time here for snapshots or something, but you want to be able to hide that. If I went to just 8 GPUs, immediately you're seeing in these regions, I'm getting communication with no computational overlap. But if I move to like TTI, for example, we're seeing that, yes, we could still hide the overlap. So you have the problem of feeding the beast that you have to solve. Now, if you remember, I said our primary goal for portability was hardware. Unfortunately, we weren't able to procure another accelerator device to test on. But there was also, so we thought, well, what if we had something, we just assumed that we had an accelerator device that had a similar performance to what we had. We would probably be running on OpenCL on that. There are some caveats with the OpenCL. To get peer-to-peer communication, we had to do some stuff where we actually went down to the host. So you will see some performance differences that we think is important to show. So again, we still have space-time grid points per second. And I'm going to move from 1 GPU to 2 GPU and 4 and 8. And you'll see that these bars will double, but I'm trying to keep that same idea. If you get weak scaling, these bars shouldn't move. So if I go between the two, you'll see some changes in the black bars are the OpenCL performance, but as you go to computational intensity, you'll see that there's fewer down there on the TTI side to the right. Then if I go from 2 to 4, now you're starting to see significant changes. And then even now, if I can show the GPUs that we have 8 for, you'll see even bigger changes, and you're also seeing that the CUDA performance is going down. Again, that's because we weren't giving it enough to compute on to hide the latency that we were using. And you'll also notice that the changes between the large versions here are significantly less, just to heighten that. Finally, I'd like to discuss the numerics. The idea was to give the user kind of a control or a dial-on trade-off between accuracy and computational cost. And so the way that we could do this is instead of just computing a set of optimized coefficients based on your velocity model, let's do multiple sets of optimized coefficients. And so that includes variable spatial order. So if we go back to this cross stencil, if you had, for example, slower velocities, maybe you want to increase the order you're using, or faster velocities, you'll decrease. So you could get something with like 12 fourth order, 10 sixth, 10 eighth order for a total of 32 sets of coefficients that you choose from before you run the wave propagation of which one you want to use. And what this can do is if you look here, you can kind of think of this diagram as an idea for performance or speed up. This is really a space-time cell size. As we go to increasing relative error, once we get beyond this point, we're getting like about a 4x factor performance. If we looked at our previous production, we were actually getting a 3x performance, and that's just on algorithm improvement. That's not actual hardware design. So that goes back to kind of Dave's talk and the keynote speak earlier, is actually optimizing for the algorithm instead of just the hardware. So how did we create these sets of coefficients? Pretty simple kind of idea. Why don't you bin them by a beginning and an end velocity, keeping track of, if you have isotropic, you can have a fast direction velocity. So you have to be aware of your time steps. And basically, you would start with your higher order stencils here, moving to lower order. And then this is kind of just a little, throw in a little bit of a curveball there. We were trying to do modular and do multiple kernel designs. Well, what if you decided to go from a cross stencil to a diamond stencil? What would your relative, your percent error be with respect to the number of bins that you're using? And here, this is our previous production versions. Our goal is to kind of get somewhere in here. This is what we ended up with our single pass. The TTI actually multi-pass ended up somewhere down here as well. But it's something that you could give the user something to play with, either get better accuracy or better computational performance. And to summarize, so we were able to get portability using Akka, and we were able to test various NVIDIA GPUs and see the performance. We tested CUDA versus OpenGL. It would be better to see other hardware, but it would be nice to have an understanding if you went to the hardware what caveats you may have moving to the OpenGL part. We did test CPUs. We did OpenMP and Serial. But we designed, again, in the beginning, I said we wanted to perform for the NVIDIA GPUs. That was what we had in the cluster. So it wasn't quite a fair comparison. The performance difference was significant, but had we designed more towards the CPU side, we think we would have seen improvements there. So you still don't solve that problem that was spoken earlier of you're still focusing towards an architecture. And we improved our software infrastructure really just by making it more modular and using inheritance, so you reduce your development time and improve your reusability of your code. We took advantage of the new computational features that were available to us, and then we implemented the new numerics where we used multiple sets of variable coefficients. And I'd like to finally end by acknowledging Scott Morton, Hess Corporation, for permission to share this, as well as NVIDIA, and Tim Warburton's group, specifically Dave Medina. He's the guy who developed Akka, but the rest of Tim's group was part of QCing and further development and helping us get to a stage where we could use it as well. And with that, I'll take any questions.
Yeah, thanks, Thomas. Mm-hmm. Any questions? While you're thinking, I do have one, probably more than one, but let's start with one. So you promised that Akka would give you the portability, and usually when you talk about portability and ease of programming, there is the expected trade-off in terms of performance. Do you have any feel for, can you quantify that, or at least qualify the the ease of programming versus handwritten, let's say, CUDA code, and also, of course, the performance differences.
Yeah, okay, so you kind of get the idea. We did spend a significant amount of time optimizing, even on the Akka side, being aware of the architecture. But if you just wanted something to work pretty reasonably fast, you get something that looks more like an OpenMP type structure. So you could kind of maybe get the 80% solution by going that direction. So that's, in that case, yeah, you would have faster development time, but I suspect you would lose in that performance. Does that answer?
Well, yeah. Ideally, I would be hoping that you can say, well, this is 80% of the speed at X% of the development time. I guess that's
yeah.
what.
I don't know that I have a number for that. We'd have to
That's
probably
fair.
track. I need more data points. So.
Fair enough. And yes, please.
Yeah, a quick question. When you post those passing speeds for forward only or for RTM?
For what?
For forward propagation
Yeah,
only or for RTM?
just a single propagation, whether it's forward or backward. So you know the backward just reverse, it's time symmetry, so a forward propagation, yeah.
But you have overhead there for the snapshots. So
Yeah, I didn't put in this because we wanted to show this for FWI as well as other things, so we didn't include snapshot time. Yeah, if you wanted to hide snapshots, that would be an issue in itself. Yeah.
Are you looking into time skewing type of scheme for those stencil?
I am not aware of time skewing, or at least perhaps in that by that name.
Yeah, I have two questions actually. When you compare in a P100, you have NVLink between each GPUs, I mean 1 to 1, or between 0 and 1 and 2 and 3?
Okay, so yeah, the 4 of them have a link between themselves, and then 2 others in the other group of 4. And I had 2 cases there. So I had the DGX where I could go up to 8 GPUs, and then I had PCIe Express, but I only had 4 to try and play with.
Okay. Next thing, have you done any tests where you have to get out of the node, where you have to use MPI now, from one node to another?
So so the idea was to pull MPI out in that case. We were designing if we did decide to hop nodes. We just never made to that point of what we would do if we had to start hopping nodes. But the idea was to stay.
How good you are going to scale if you bring the MPI?
Yeah, so that's part of it was we didn't want to go to other nodes. We focused on not going to other nodes.
Okay. Thanks.
So so there's 2 components now that when the portability comes, because you now have protected yourself from the hardware. But what about when Oka is replaced behind you and improved? Does that impact your code?
Yeah, so that could. That's a risk you take. So we were looking at mitigating the risk, and what we did, were we going to have to now maintain our own, Hess Akka, for example, or something like that? Yes.
Okay, let's thank Thomas again.